Hi everyone, this is your last lesson for this course, lesson 4.6. And we're going to use the Laplace transforms that we talked about in our last lesson. And now we're going to solve differential equations with them. So this whole last unit has been focused on solving differential equations. And this lesson is going to be no different. Because now that we've introduced Laplace transforms, we have a couple other identities that I'm going to introduce to you alongside it to help you with solving differential equations. So remember, our differential equation often looks something like this. We had a second derivative, okay? Sometimes we had a first derivative with a constant behind it. And then we had, some function of y, and that was equal to something over here, okay? Let's say it's sine of x. We know how to find the Laplace transform of a function, or the Laplace transform of something like sine of x. But there's two more identities we need to know: how to solve the Laplace transform of the first derivative and the Laplace transform of the second derivative. Well, if we go back to basics, the Laplace transform, if you remember all the way back to the first part of the previous lesson, 4.5, it was the integral from 0 to infinity of e to the exponent negative st, and originally it was f of t dt. So for the derivative, what we do is we just replace, because we're finding the Laplace transform of the derivative, which you can write as f prime, or dy by dx, or y prime, however you want to write it. And that's just simply equal to the same integral, except we replace f at t with f prime at t with its derivative. Now to solve this, you actually would solve it using integration by parts. I'm not going to run you through how it's solved using integration by parts. I don't feel that that's an important piece that you need to solve these equations. Instead, I'm going to explain to you what identity comes out of it. So your first identity for the first derivative, remember, I'm going to write first derivative, is that the Laplace transform for the first derivative is equal to s times the Laplace transform of the original function, f, minus the original function if you substitute in 0, so f at 0. Now you can do this again and find the Laplace transform of the second derivative, again using similar methods. And what you obtain is the Laplace transform of the second derivative of a function is equal to s squared times the Laplace transform of the function minus s times the function at 0 minus the derivative at 0. Okay? The reason this is so important to know these identities is if you just look at this initial equation, okay, and it has a second derivative, a first derivative, the normal function. If you try and take the Laplace transform, you're going to have three different ones. You're going to have the Laplace transform of the second derivative, plus the Laplace transform of the first derivative, plus the Laplace transform of the original function, right? Because you can take the Laplace transform of each one of these individually. Remember when we talked about what was called the linearity property. What these do is now, instead of having three separate functions here, we actually have all of them with just the Laplace transform of the original function. Okay, so we use these and we substitute them into the differential equations so that we can get just the Laplace transform. We use that and we get the Laplace transform on one side of the equation, everything else on the other side of the equation. And then remember, we can do the inverse Laplace transform to find that original function. So I wanted to show you these identities. They're obviously provided to you on your formula sheet. But I feel like the best way to show you how these work is to do three different examples. Okay, each of them are a little bit different in how they're approached. The last one has more relevance when it comes to circuit analysis, okay? So let's start with our first question. Solve the differential equation y double prime plus y is equal to sine of t if y at 0 is 0 and y prime at 0 is 1. So we see here we have a second derivative, the initial function, and a sine function on the right-hand side. So I'm going to write all of the properties that we have, okay, just so that you're aware of kind of what I'm going to use as my starting point. So first, remember, whatever we do to the left-hand side of the equation, we can do to the right-hand side of the equation. So that means we can technically take the Laplace transform of both sides. And remember, the linearity property is an important one that we use here, because it's the Laplace transform of a first function plus a constant, or times a constant, plus a second function times a constant, so a times the function f plus b times the function g, can actually means you can take the Laplace transform of each function individually. So we have a times the Laplace transform of the function f plus b times the Laplace transform of the function g. The second piece of this was that you can move the constant a and b outside of the Laplace transform, just like we've done with derivatives and just like we've done with integrals. Okay, so that's the first piece that you're going to see used. The second one is the first identity that you saw in the last slide, and that was the Laplace transform of the derivative of a function is equal to s times the Laplace transform of the original function minus the original function at 0. So I have f at 0 there. In this case, we have a function y of 0. Okay? And in this case, we also have a second derivative. We don't have the first derivative, but we have the second derivative. The Laplace transform of the second derivative is equal to s squared times the Laplace transform of the original function minus s times the original function at 0 minus the derivative, the first derivative, not the second, of the function at 0. So knowing this, I'm going to start this question off by taking the Laplace transform of both sides of this equation. Okay? And I'll change to a different color. So we'll leave all of these here so you can see them. So we have the Laplace transform of the left-hand side, remember, using the linearity property. So we have the Laplace transform of the second derivative plus the Laplace transform of the original function y is equal to the Laplace transform of sine of t. Okay? Well, using what we know for our Laplace transforms, number 6 in our table is the Laplace transform of sine of at. And that's equal to a divided by s squared plus a squared. So this is just sine of t, meaning that a is 1. So we can actually start filling each one of these in using these identities. So the Laplace transform of the second derivative, substituting in this equation here, is s squared times the Laplace transform of the original function minus s times the original function at 0 minus the derivative of the function at 0. And then we have plus, again, the Laplace transform of the original function y. So I wrote f here, this should say y. And that's equal to the Laplace transform of sine of t, which is 1 divided by s squared plus 1. That's using a, remember back to here, on the top right, a is 1 because we have just sine of t. So now we can do some rearranging, and we can also do some substituting because we know these 2 points, y at 0 and y prime at 0. I used f at 0, but again, it's the function, so it doesn't matter if it's f or y. Normally, those points will be given to you in these questions. So I'm going to do 2 things. I'm going to rearrange so that we have all the functions with the Laplace transform together, and I'm going to factor them. So we have the Laplace transform of y, and what we're left with is what's behind this first term, which is s squared, and this last term, okay, which is plus 1. All right, so that's our first two, and I like to cross them out when I'm done with them. Then we have minus s times our function at 0, which you remember back to here is 0, minus our derivative at 0, which is 1, so minus 1. And that's all equal to what's left on the right-hand side, 1 over s squared plus 1. Okay? So, using this, we can cross a few things out. We have the 0 times s, which is 0. Okay, actually, I'll do it in a different color. We can also take this negative 1 and move it to the other side of the equation. Okay? So we have s squared plus 1 times the Laplace transform of the original function is equal to 1 divided by s squared plus 1 plus 1. So now we can solve for just the Laplace transform on its own by dividing both sides by s squared plus 1. Okay? I will move my solution to here. What we're left with, this will cancel, so we have the Laplace transform of y is equal to, well, we have the first term, 1 divided by, we have an s squared plus 1 and another s squared plus 1 because we just divided by it. So that gives us s, sorry, that's a bad s, s squared plus 1 all squared. And our second term, we have plus 1 divided by s squared plus 1. Okay? So, now both these are separate. And remember, we can find the inverse Laplace transform of each of these functions once we figure out what form they fit in terms of our table. Okay? So our second item here, 1 divided by s squared plus 1, that actually fits number 6. And number 6 is that sine of at, actually I'm writing it, when number 6 is actually sitting right here. Okay? A divided by s squared plus a squared. So a is 1 in this case. So we know for this one, it must be sine of at. The second one takes a little more figuring out to get there. So in the denominator, we have an s squared plus a squared. Okay, and that's all squared. And we don't have an s term in the numerator. Okay, we just have some value of a. If we look at our table, the only one that satisfies that is number 15. And number 15 is sine of at minus a times t cosine of at is equal to 2 times a cubed divided by s squared plus a squared all squared. Now that doesn't quite fit, right? Because we have a 2 there. But it can fit if you look at back to our original equation, we need to somehow obtain a 2 in here. And we can do that by multiplying the numerator and the denominator by 2. Okay, because again, 2 divided by 2 is 1. So if we look at this, I'm going to rewrite that just so you can understand it. So we have 1 divided by s squared plus 1, all squared. And I'm going to multiply it by 2 over 2, which is the same as multiplying it by 1. Plus the second term, which stays as 1 divided by s squared plus 1. So now what we can do is we can rewrite this by placing the 2 in there. And we get the Laplace transform is equal to 1/2 times 2 divided by s squared plus 1 squared plus 1 divided by s squared plus 1. Okay, so the difficulty with those is you have to look at your Laplace transforms and say, well, where does this fit? And if it fits only in a certain one, then you might have to manipulate it if it corresponds to certain numbers in the numerator and denominator. And I really stress numbers, okay? Not necessarily because there's an S term missing, but because there's a number missing. You have to do this type of manipulation to get that number in there so that we can use the Laplace transform. Again, the reason this works is remember back to our linearity property, which is sitting up here, right? You can take that Laplace transform or find the inverse Laplace transform if you have a constant multiplied by one of the known Laplace transforms, okay, which this became a known Laplace transform, okay? So it definitely takes some practice for you to start kind of visualizing and seeing that, okay? So if you don't necessarily see it in this first example, we have 2 more examples that we're going to do in this lesson, as well as examples when we have our tutorial sessions. So take your time when you're looking at these, make sure you do a lot of the practice problems, okay? So now if we're going to find the inverse Laplace transform, okay, it's equal to 1/2 times the inverse Laplace transform of the first function. Remember we said it was number 15. So sine of AT minus AT cos of AT, which in this case is just sine of t because our a is 1, minus t cosine of t, plus the Laplace transform of our second function, okay, which is just sine of t. So now we can do one more simplification. We have a 1/2 sine of t and a sine of t. So we can add those together. And we get the Laplace transform is equal to 3/2 sine of t minus t cosine of t. Okay, so you can see we have no unknowns in these. That's the benefit of Laplace transforms, is it finds the particular solution where we don't have just these constants that we haven't solved for. Okay. All right, so our second example. This one you're going to see is going to bring us back into partial fractions. Solve the differential equation, d squared y by dt squared plus 3 dy by dt minus 4y is equal to 0. If y at 0 is 4 and y prime at 0 is 2. Okay. So once again, for this one, in the first example, I wrote the Laplace transform identities that we went over in this lesson. I also wrote the linearity property. I won't write them here, but what I do encourage you to do is I encourage you to have the formula sheet with you for this, because I do list those. All right, so I wanted to emphasize them in the first example, but now I'm just going to show you how to use them in solving. So we're going to do these same steps that we followed in the first example. We're going to take the Laplace transform of both sides. So the Laplace transform of each individual function, remember because of the linearity property. So the Laplace transform of the second derivative. Sorry, I write dx squared out of habit, but it's dt squared, so dy by dt squared, plus 3 times the Laplace transform of dy by dt, minus 4 times the Laplace transform of the function y, and that's equal to the Laplace transform of 0, which, as you can guess, anything with 0 is typically 0, and it is also the case here. So using the identities we know, I'm going to substitute in for the Laplace transform of the second derivative and the first derivative. Okay, so for our first one, we get s squared times the Laplace transform of the initial function y minus s times the original function y at 0 minus y prime at 0, or the first derivative of the function at 0, plus 3, remember, times the Laplace transform of the first derivative, which is s times the Laplace transform of the initial function y, minus y at 0, minus 4 times the Laplace transform of y, and it's all equal to 0. Okay, so long equation, we'll simplify it and kind of make it a little bit less hectic now. So we can substitute in y at 0 is 4 and y prime at 0 is 2. If we do that, we get s squared times the Laplace transform of y minus s times y at 0, which is 4, minus y prime at 0, which is 2, plus I'm going to multiply in this 3 at the same time that I do this. Okay? So we get 3 times s times the Laplace transform of y minus 3 times y at 0, which is 4, minus 4 times the Laplace transform of y, and that's all equal to 0. Okay? So now I can start to group things together. I'm going to group together everything with the Laplace transforms, or Laplace transform of y, and then I'm going to group together kind of the remaining terms, and we'll see what we're left with. So we have the Laplace transform of y as a common factor, and we have our first term, which is s squared, plus our second term we have, which is 3s here in the middle, minus 4. And again, I like to cross these out just so that I don't miss anything, okay? Next, we have minus, oh, I'm still in blue, minus the 4s term we have here. And then we have minus 2, minus 12, okay? So we get minus 2 minus 12 is minus 14. And that's all equal to 0. So remember, I want to solve for the Laplace transform of the original function on one side. So I'm going to move this second piece to the other side. And then we can divide both sides by this term that's multiplied by the Laplace transform and move on to our next step. So we'll start by moving those pieces over. So we have the Laplace transform of y times s squared plus 3s minus 4 is equal to 4s plus 14. So getting the Laplace transform by itself, we divide both sides by s squared plus 3s. That's a terrible s. Minus 4. Okay, so they cancel on this side. And we're left with the Laplace transform of the function is equal to 4s plus 14 over s squared plus 3s minus 4. Which, luckily for us, we can factor the denominator. So we get 4s plus 14 divided by, this factors to s plus 4 and s minus 1. Now this is where our partial fractions piece comes in. Okay, so we have two items sitting in the denominator. So we can write them as a divided by the first term, s plus 4, plus b divided by the second term, s minus 1. Now remember, when we solved this, we multiplied both sides by everything here in this denominator, and then we're able to solve for the fractions a and b. Okay? So if we do that, we're left with, on the left side, 4s plus 14. And on the right side, we have a times our remaining term, s minus 1, plus b times s plus 4. Okay? And that, if you remember, comes from multiplying both sides, okay, by s plus 4 and s minus 1. So on this side, those will cancel. On the right-hand side, for a, the first two cancel, s plus 4, but the s minus 1 does not. For the second fraction, the s minus 1 cancels, but the s plus 4 does not. So I realized I went through that a little bit quick, so that's why I wanted to show you that. That's how we end up with what we have here. So I'm just going to draw a line here so that we can give ourselves a little more space. So now if I multiply this out, I get 4s plus 14 is equal to a times s minus a, multiplying that out, plus b times s plus 4 times b. Okay? Now remember, we looked at combining all the terms that had the same s or s squared term to figure out, to solve for the partial fraction at terms a and b. So for the terms with an s behind, or an s in front of it, we have 4 on the left-hand side. On the right-hand side, we have a plus b. For just constants, on the left-hand side, we have 14. On the right-hand side, we have negative a plus 4b. Okay? So looking at our first item, if we solve for a, we get that a is equal to 4 minus b. So if we substitute it in, we get that 14 is equal to negative times what a is, 4 minus b, plus 4b. So we have 14 is equal to negative 4 plus b plus 4b. So to solve for this, we can move the negative 4 to the left-hand side, and we can add the two b terms together. So if we bring the negative 4 to the other side, we have 14 plus 4, which is 18. And that's equal to b plus 4b, which is 5b. Dividing both sides by 5, we get that b is equal to 18 divided by 5. So what this means is a, if you remember, is equal to 4 minus b, which is 4 minus 18 divided by 5. And you can either put these in your calculator and convert it to a fraction, like I've showed you in the past, or you can multiply these out as fractions. If you do that, you get a is equal to 4 is the same as 20 divided by 5 minus 18 over 5, which gives you 2 divided by 5. Okay, so a is 2 over 5 and b is 18 over 5. So what that means is, going back to our initial partial fractions, we have the Laplace transform of y is equal to a, which is 2 over 5, times what we had, 1 divided by s plus 4, plus b, which is 18 over 5, times 1 divided by s minus 1. Okay? Now both these, s plus 4 and s minus 1, fall into number 3, okay, which I'll write here at the top. And number 3 is that e to the negative at is equal to 1 divided by s plus a. So, using that Laplace transform, finding the inverse Laplace transform of y, which is just y, is equal to 2 over 5, and this one becomes e to the negative. Well, here we have a is 4, so 4t, plus 18 divided by 5, and the second one is a negative number, meaning that it's going to be a negative value for a. So we get e, and then we have negative times negative 1 times t, or you can write that as just e to the exponent t. Okay? So a longer way to solve it, especially using partial fractions, but a lot of times with these partial fractions, you get to these solutions that will usually lead to a function of e or a function of sine or cosine. Okay, so I'm just going to give you that as a suggestion. is when you're doing these partial fractions, those are typically what you're going to come up with when it comes to your solutions. All right, so this is our last example, your last example you're going to have to hear from me on YouTube, at least in this course. And I thought I would do one. I don't usually like to use the ones directly from the textbook, but I felt this one was very relevant to give you, especially because this is kind of a major area to use Laplace transforms for, okay, circuit or network analysis. So this is a basic example of using them. You're going to see likely far more advanced versions when you're in your other classes. But I do want to just give you this introduction and also kind of have this video here for you if you need to use it in later courses. Okay, it'll still be available. It might be listed as private, and if that's the case, you can just send me an email and I can give you the link to it. But besides the point, I'm digressing a little. Our last example says an electric circuit in an FN transmitter contains a 1 Henry inductor, 4 ohm resist, and a 4 ohm resistor. It's being tested using a voltage source of 6 sine of 2t, okay, so fluctuating voltage. If the initial current is 0, find the current I as a function of time t using the following equation. L di by dt plus I times R is equal to the voltage V. And I've given you the diagram here, which is the same diagram, like I said, from your textbook. So like I said, I don't usually give you questions that directly match examples from the textbook, but I'm going to go over this in more detail than the textbook does. So I'm hoping that that helps you when you're looking at this style of question. So we start with this initial equation, and we can start filling in data. Okay, we know the value of L, we know the value of the resistance, R, and we know the value of the voltage, V. So I'm going to start by substituting those values in. So for L, it's just 1, so we can just pretend it's not there. So we have di by dt. Plus, our resistance is 4, so we have 4 times I. And that's equal to our voltage, which is 6 sine of 2t. So now I'm going to take the exact same steps, find the Laplace transform of both sides. So we have the Laplace transform of the derivative, di by dt, plus 4 times the Laplace transform of the initial function I. Remember, we're looking for current. And that's equal to 6 times the Laplace transform of sine of 2t. Okay, again, I can remove the constant here because of our linearity property. So there's two Laplace transforms we can actually substitute in for. The sine of 2t, remember using number 6 on our table, which is sine of at is equal to a divided by s squared plus a squared. In this case, a behind here is 2. So we can actually rewrite that as 2 divided by s squared plus a squared, which is 2 squared, or 4. Okay? We can also write the Laplace transform for the derivative, remember using our identity. So substituting these in, we get s times the Laplace transform of the function I minus the original function I at 0 plus 4 times the Laplace transform of I is equal to 6, and again now we're going to multiply it by the Laplace transform we just solved for, 2 divided by s squared plus 4. Okay? So I'm going to do the same things here. First, we know the initial current is 0, so that means this term will cancel. So on the left-hand side, we just have two functions remaining. Both have the Laplace transform with them, so we can factor that out. So we have the Laplace transform of I times what's remaining, which is s plus 4. And that's equal to, on the right-hand side, we can multiply the 6 in if we choose to. I will multiply it in. You'll see why we may have to remove it out at the end. But we have 12 divided by s squared plus 4. So now, to solve for just the Laplace transform, we're going to divide both sides by s plus 4. And we get the Laplace transform of the function I is equal to 12 divided by s plus 4 times s squared plus 4. Okay? So now remember, we can write this as partial fractions. You're always going to get to this stage, or at least in most cases, and move it to partial fractions. But we have a second order function here, right? Because it's s squared. So remember, there's one more step to do. And what you do is when you're writing it as partial fractions, you have a divided by the first term, which is s plus 4. Remember, since the second one is second order, our numerator has to be first order, which is b times s plus c divided by s squared plus 4. Remember, when you had those functions that were quadratics, you had to make sure you had a function of s in the numerator. In some instances, one of those terms, b or c, may very well be 0. But because we're looking at a basic form to solve with partial fractions, we have to keep that in there. Okay? Now, following the same steps, we can multiply both sides by everything in that denominator, s plus 4 and s squared plus 4. Okay, again, doing that to both sides. If we do that, I'll move my solution up here. On the right-hand side, we have just the number 12 because they cancel. On the left-hand side, we have a times our first one. We have the s plus 4 cancel, but the s squared plus 4 does not, plus bs plus c times the s squared plus 4 cancels here, but the s plus 4 does not. Okay, so I'll erase those just to give us a little bit more space here. So multiplying this out, we get that 12 is equal to a times s squared plus 4 times a, plus distributing all these terms out, we get b times s squared plus 4 times b times s plus c times s plus 4 times c. So now we're going to end up with 3 equations and 3 unknowns. Okay, so we have in our first, we have the s squared terms. So on the left-hand side, we have 0. On the right-hand side, we have a plus b. And again, I will cancel these as I go. For the second equation, I'll also do the equations in colors so we can see them a little better. For the second equation, we have terms with s. So on the left-hand side, we have 0 once again. On the right-hand side, we have 4b plus c. Our third equation, we have constants. So on the left-hand side, we have the constant of 12. On the right-hand side, we have 4a plus 4c. And just to make the math a little bit simpler, you can see that everything in the last equation is a multiple of 4. So we can divide all the terms by 4. Again, as long as you do something, the same thing to the left-hand side of the equation as you do to the right-hand side. So we're left with 3 is equal to a plus c. Now this one gets a little bit complicated, and it's because we have to do multiple substitutions. Okay, so we'll start by just solving the first equation. So we have a is equal to negative b. So we can plug that into the second equation, or I guess we can plug it into the third equation. That'll probably be the better option. If we do that, we get that 3 is equal to a, which is negative b plus c. So solving for c here, we get that c is equal to 3 plus b. So now going back to our second equation just has b and c. So I'm going to substitute in 3 plus b for the c term. If I do that, I get that 0 is equal to 4 times b plus c, which I can replace with 3 plus b. Okay? Now if I do that, all right, I can add the 4b plus b together, and we have 0 is equal to 5b plus 3. Moving the 3 to the other side, we get negative 3 is equal to 5b, or solving, we get that b is negative 3 over 5. Remember, we have that a is equal to negative b, so that means that a must be equal to positive 3 over 5, because going back to our equation here. So now we can also solve for c, because remember, we have that c, oh, that's in yellow, that is hard to see. C is equal to 3 plus b, remember going back to here, which is 3 plus b, which is negative 3 over 5. And if you solve for that, okay, 3 plus negative 3 over 5 is 3 minus 3 over 5, okay, which gives us a value for c of 12 divided by 5, okay? So now we have all three terms. Remember, back to our partial fraction here. I'm going to write it out here, and then we're going to go to the next slide, and I'm going to use what we have left. So we have the Laplace transform of I is equal to A, which is 3 over 5 times 1 over s plus 4. Then I can't separate this one out as easily yet, so I'm just going to write it exactly as it is. Bs plus c, which is negative 3 over 5 times s. It's a terrible 5, I'm sorry. Plus c, which is plus 12 over 5. And that's divided by s squared plus 4. Okay, so I'm going to take that Laplace transform. We're going to go to a new slide, and we'll start with that to determine our final solution. So remember, we have the Laplace transform of the function I, and that's equal to 3 over 5 times 1 divided by s plus 4, plus negative 3 over 5 times s plus 12 over 5, divided by s squared plus 4. So my next step is I'm going to break this second piece here into two functions, okay? Because we have items in the numerator added together, so we can break this up into two separate fractions as long as they have the same denominator. So this becomes the Laplace transform of the function I is equal to 3 over 5 times 1 over s plus 4. That hasn't changed. Then we have minus 3 over 5 times s over s squared plus 4. Okay, so that's using this first term. I just took the coefficient, the 3 over 5, and put it outside of the brackets. Again, I like to take the constants out just so I can see the kind of cleanest form of the function to compare it to our Laplace transform table. Then we have plus 12 over 5 times 1 over s squared plus 4. Okay? So now we need to figure out if these fit within certain Laplace transforms that are sitting here in our table. And the 1 over s plus 4, you've seen that one multiple times. That corresponds to number 3. Remember, number 3 is e to the negative at is equal to 1 over s plus a. The second function actually, once again, falls into one that we might have seen before, number 5. So number 5, okay, is cosine of at is equal to s over s squared plus a squared. So we have an s term in the numerator and an s squared plus 4, which 4 is just 2 squared. Our third one's a little bit different, Okay, the only one that falls close to it is number 6. But number 6 is sine of AT is equal to A over S squared plus A squared. So we know that in the denominator, A squared is 4, so A is 2, meaning we have to have a 2 in this numerator. So we have to, again, like we did before, do a bit of manipulating. So we have to break this 12 up into 2 terms so that we can have a 2 in this numerator. So we can have 6 times 2 is 12. So we can rewrite this, and I'll erase this and rewrite it, as 6 over 5 times 2 over S squared plus 4. Remember, because if you multiply those out, 6 over 5 times 2 is equal to 12 over 5, which is what we had initially. All right? So always keep in mind that there's usually some kind of number manipulation, and I always stress number manipulation, to get them to match exactly. So now that they're matching Laplace transforms we have in our table, we can find the inverse Laplace transform, which is just going to be I on the left-hand side. That's equal to 3 over 5 times the Laplace transform of this term, 1 over S plus 4, which you remember is e to the negative 4t, because in this instance, A is 4, minus 3 over 5, and for the second one, it was cosine of AT. Again, in this instance, A was 2, remember? Because when the denominator, we have 4, which is 2 squared, because following the cosine transform, it's squared. Plus our last one, which is 6 divided by 5, times the sine of 2t. Okay? Remembering that A is 2, because that's in the numerator, and in the denominator, 2 squared is 4. Okay? So this becomes our final solution. Okay, so that is our function for current. All right? Okay, so that's it. That is our last lesson for this course. I've given you some practice problems, and I've also given you a note here. Okay, so in my third example, I gave you the equation for that specific circuit. The additional questions here, 29 to 32 and 35 and 36, do not give you the equation. So you're more than happy, or I'd be more than happy to have you try these problems. You likely won't see one like that where I make you derive the equation on your test, but it would be good practice for you to look at those, especially if you're looking at more advanced versions of these Laplace transforms. Okay, so give these questions a try, and we can always go over them. If you have questions, send me an email or send me a message on Teams. Thanks everybody for watching all these videos. I hope they helped you in this course, and if you are continuing on and need them for further courses, you can always ask me for the links again if you lost them. Okay, so thanks everybody.